In this problem, we are going to look at the strategy for determining the complete chemical structure based on a set of NMR and or mass spec data. So in this particular example, we're given the information that mass spectrometry analyses supported a particular molecular formula, C5H9O2Cl, and we are also given the one proton NMR spectrum for that molecule as well. You will notice in this proton NMR spectrum, we're not seeing the entirety of the range of the x-axis. We're only seeing from about 1 to 4 ppm. And generally the reason for this cutoff is so that we can zoom in on where we actually see signals in the spectrum. The parts that are cut off, you can assume there are no signals within that range. So the most downfield signal, in other words, in this spectrum is right there at around 4.2. And we can conclude from this NMR spectra that we have a grand total of 4 distinct chemical environments of protons because we have a signal here, 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 and here. And another piece of information that I want to highlight and point out to you is these values up at the top represent in hertz the locations of the signals on the x-axis. And this is useful because this will give us information about the coupling constants. We can pull out our calculator and do some subtraction here to sort out what the coupling constants are and multiplicities of these different signals. Now, be aware that at the top of spectra, you will commonly see 2 types of information. One is that you may see the integrals listed up at the top that indicate how many carbons, or rather how many hydrogens, represent a particular signal. You may also see at the top the chemical shift value indicated, or you can see these coupling constants in hertz. And you'll have to deduce which of those you are looking at generally. In the case of coupling constants, you will notice that these values are in the thousands, much larger than possibly the integral values of these signals are, much larger than the chemical shift values are. So we can deduce that this information at the top has to represent our hertz values of these different signals that we are seeing along the x-axis. Down at the bottom, on the other hand, right here where we see the number 2, for example, 2.06, 2.04, etc., what that's representing to us is the integral values. And so if we add up those integrals, that is 2 plus 2 plus 2 plus 3, that should equal out to the total number of hydrogen atoms that are in this particular structure. And looking back, pulling onto this screen here, our molecular formula had 9 hydrogens in total, and you will notice that the sum here of these integrals adds up to 9. And that should generally be the case. The only exception is occasionally if you have a hydroxy group or an amine group that has a hydrogen bonded to it, those hydrogens are what we refer to as exchangeable protons because they can be lost and gained quickly in acid-base reactions. And so those often, as a result, are not seen in the NMR spectra. Instead, they are invisible. So if you notice that there is a difference in the number of the integral down here versus your formula, what it usually means is that one of your protons is part of a hydroxy group or an amine group, so that it is an exchangeable proton that will be invisible in many NMR experiments. But here, everything adds up. 2 plus 2 plus 2 plus 3 equals a grand total of 9 protons. So all of those are accounted for based on our integral values. And so now our job is to go in and use these data to piece together how the C5H9O2Cl given molecular formula is actually arranged. The 3 pieces of data that we want to focus on for this are, we want to focus on the chemical shift. That will give us clues about the environment of each individual proton, where the chemical shifts that are further downfield, representing the d-shielded protons, represent protons that are in a more electron-poor region. and we can use our chart of expected chemical shift values in order to deduce some information about functional groups, about what types of atoms are likely bonded at each position here. So chemical shift is one piece of information that we will rely on. Another piece of information is our multiplicities. And for these multiplicities, we can also look at our coupling constants, those Hertz values up here, and their expected values. And then thirdly, we want to look at the integral values, because the integral values, highlighted in red at the bottom, represent how many hydrogens make up that particular signal. So 2, 2, 2 versus 3. So let's go ahead and get started with trying to sort out the structure of this molecule. So what I would recommend doing is start with one signal from your NMR spectrum and try to build the molecule from there. Like take one signal and determine how far can you piece together the structure of the molecule based on that one signal, looking at its chemical shift, multiplicity, and integral. And then hopefully, eventually you have enough sub-pieces of the molecule that you can ultimately stitch it all together, because you will find parts and pieces that go together. So I'm going to start with this signal over here that integrates to a value of 3. Generally speaking, I love integrals of 3 because typically, the vast majority of times when you have an integral of 3, what that is representing is a methyl group. And so I'm going to sketch in a methyl group here, a CH3 group, and keeping in mind that this is a 3 proton signal, I'm just going to label it 3H, just doing my scratch work here. And this has within it splitting of 3, meaning that this is a triplet. And we can tell it is a triplet in two ways. One, if you look closely, you can see the 3 subpeaks in here. The other is if you look up top here, you see these 3 values for the 3 Hertz values representing the location of each of the subpeaks within that. And so that suggests 3 subpeaks indicating a triplet. So this is a 3 hydrogen triplet we have tentatively assigned as a methyl group. And in order for a methyl group to show up as a nice clean triplet like this, that means that methyl group needs to have 2 vicinal hydrogens, which I'm going to plug in just as CH2. And the fact that this is a nice, very distinct, very even, nice triplet with a signal here and here that are relatively symmetrical, flanking it with the 1 to 3 to 1 expected ratio, or I'm sorry, 1 to 2 to 1 ratio, 1 to 2 to 1, giving nice, perfect looking triplet. We expect that that CH3 is directly bonded to a CH2 group. So our CH2 group is right here. So we have our CH3 directly bonded to a CH2 group is what we're hypothesizing is going on here. Now, for that to actually be the case, we need to find some signal within the rest of this spectrum here that could fit this paradigm of being a CH2. So all 3 of these would be a candidate based on the integral, because all 3 integrate to 2, meaning they represent 2 hydrogen atoms. So what else can we look at here? Well, we could look at the multiplicity. The CH2 group is going to have a minimum multiplicity of being a quartet, because if the only vicinal hydrogens are the ones on the methyl group, using the n+1 rule, 3 plus 1 makes 4, which would mean this would have to be a quartet. It's also possible there's other hydrogens vicinal coming in these other directions. And so it needs to be at least a quartet. And so as a result, we can actually rule out the signal here at 2.8 ppms because it's only a triplet. We can rule out the signal here at 3.75 ppms because that's only a triplet. And then we have the signal over at about 4.2, which does indeed very much look like a quartet. And it even has the 1 to 3 to 3 to 1 characteristic ratio of the intensities there. And we can further verify that's a quartet because if we look up here at the top, we see the 4 Hertz values labeled there, indicating we have 4 peaks showing up here. So that's what I'm going to plug in as our CH2 group for now, tentatively speaking. And by the way, NMR is very much a problem-solving, puzzle-solving adventure. And so trial and error is definitely something that goes on every time I or anyone else solve an NMR structure, is that you try something, you see if it works. If the hypothesis you made and sketched out matches the data, then you carry on with it. If it doesn't match the data, then you go back to the drawing board and move around some parts and pieces until you get everything to click together. So far things are clicking together in this problem because our CH2 group, we said needed to be at least a quartet, and we do indeed have exactly a quartet right here at a chemical shift of around 4.2. So with that, what I am proposing is that the 2 signals here as our most downfield signal at 4.2, and way over here is our most upfield signal at 1.25. I am proposing that those are coupled to one another because our 3 hydrogen signal over here, our CH3, was a triplet, so we said it had to have 2 vicinal hydrogens, so I drew in a CH2. And then thinking about that CH2, it would have to be coupled to the CH3 because it's vicinal, and so that would make it be expected to be a quartet at least. And so we come over to here and we see a quartet. So we establish that as CH2 as the signal that we are seeing over there. We can do one other thing to confirm this, which is that we can look at the coupling constant between the methyl group, CH3, and our methylene, CH2. Since those are coupled to one another, we should see that they have the same coupling constant in both directions. Since coupling is reciprocal, if one of the protons is coupled to another, meaning the spin-spin splitting pattern is existing, then they are coupling at the same frequency in both directions. And so what we can do is we can come up here to our coupling constant, and we can sort out what the Hertz value is for the coupling there. And the way that we do that is we can subtract from one another any 2 of these adjacent values. So we can subtract 2095, and I can even get that down to the decimal place, 2095.8 minus 2088.6, 2088.6 gives us 7.2 Hertz. And we would see a similar value here if we subtracted 2081.4 minus 2074.4. We would get a similar value there within a margin of error. And then we come over to our triplet over here. And there are coupling values, our J values. We can calculate here as 637.2. That is the furthest downfield of those subpeaks, minus 630.0, and that gives us 7.2 as well. And so the fact that these coupling constants are equal for the 2 groups suggests that they are indeed connected to one another. They are indeed responsible for splitting one another. So that provides additional evidence here in terms of the multiplicity, specifically looking at the splitting pattern of a triplet versus a quartet, and digging a little bit deeper just to confirm, looking at the coupling constants and finding those are the same suggests that these 2 groups, the CH2 group and the CH3, are indeed directly connected to one another. So with that then, we have our ethyl group in place within this molecule, and we have to keep piecing together what's going on here in our structure. Well, looking at our CH2 group is awfully far downfield. It's the furthest downfield of all the signals in this spectrum. And so what I would think when we see something downfield is that it's likely bonded perhaps to a heteroatom. So looking at our structure here, we have 2 oxygens and a chlorine. And if we think about our chart of expected chemical shift values, if we put a chlorine atom or an oxygen atom in here, would we expect the chemical shift of this CH2 to be at about 4.2, which is where we see it. So let's take a look at our chart of expected chemical shift values, because I don't expect you to have that memorized. I certainly don't. And we're going to look and see whether the expected chemical shift for this CH2 bonded to a chlorine or an oxygen would be expected to be at 4.2, because that might help us piece together what's bonded to that CH2. Now what I've done is brought in our chart of proton NMR chemical shift values. And keep in mind that you can access this information in the bundle of handout materials for this unit on NMR. You'll definitely want to have this handy when it comes time to solve problems and take the quiz and things like that. And so we're trying to address here whether this is likely a chlorine or an oxygen bonded to the CH2 or none of the above. We find it's the most downfield signal, so we think it has to be one of those possibilities. So let's take a look. We're at 4.2 here. And as we look at our chart of expected chemical shift values, if we have a CH, remember that H that's in red there in our chart of expected values is the one that we are measuring the chemical shift of. If that carbon-hydrogen bond is directly bonded to a chlorine, we expect it to be between 3 and 4 ppms. We're a little too far downfield for that, so maybe we're barking up the wrong tree here. Maybe we are looking for something else here as being a better fit. So continuing on to take a look at possibilities, another possibility is that that CH2 could be bonded to an O, such as an ether molecule. And the ether is lining up pretty well with our alkyl halide or alkyl chloride to be specific. The ether starts a little bit further downfield, it goes a little bit further downfield, but I don't think based on this information so far that we can necessarily say for sure whether it's a chlorine atom or an oxygen atom right here. So we're going to leave that dangling a bit, and we'll come back to it later once we have perhaps some other clues assembled to sort this out. So now what we can do is we can come on in and take a look at the other 2 signals within our proton NMR spectrum. And we can try to sort out where those are going to fit into the puzzle. So these both integrate to 2, which suggests to me that each of them represent CH2 groups. Either that or we have some symmetry in the molecule going on. But so far it's looking like there's not overall symmetry in the molecule because we have a CH2, CH3 group here, and we don't seem to have that duplicated anywhere. So I'm going to label these as 2 different CH2 groups. And we're going to ask where could those fit into the puzzle, into the equation here. So the CH2 that is further downfield right here is a triplet. And that triplet, when we think about the chemical shift of it, we would conclude that it is likely bonded to either an oxygen or directly bonded to a chlorine when we look at what we have available in our formula up top here, and we think about the chemical shift being right there in that range of having a chlorine bonded to it or being part of a carbon-oxygen bond there. So that leaves that as a possibility. And then we have our other CH2 group over here between 2.7 and 2.8. And when we look between 2.7 and 2.8 in our data here, that puts us right around in here. So it's a couple of groups that have a nitrogen atom as I go up in the table. That's definitely not it since we don't have that. Possibly a carbon-hydrogen bond that's directly bonded to a carbonyl. Iodine-containing group, nope, can't be that. Aromatic, not going to be that because we don't have enough carbon atoms to make an aromatic ring and then have a carbon off of it. We have an alkyne group, so we could think about that possibility. And then we have a sulfide, which is not going to work because we don't have that in the molecular formula. So this signal here that is between 2.7 and 2.8, we would conclude is perhaps a CH2 directly bonded to a carbonyl, or it's a CH2 that one might think of as being part of an alkyne group. But there's a problem with what we just drew here. So we can rule out the alkyne group because the alkyne group at most can have one hydrogen as the integral here, because otherwise, when we look at this structure, we are going over the octet rule there on this carbon. And this integrates to 2. And so therefore, it has to be 2 protons here. And so the alkyne group that I'd originally highlighted as a possibility over here, we need to get rid of that. And so really the only thing that matches based on the chemical shift is that we have hydrogens on a carbon that is directly bonded to a carbonyl group. So that red hydrogen in our chart is the one we're measuring, and it's separated by one bond from the carbon that's bonded to a carbonyl. So it could be something like this as a hypothetical structure. And we do have 2 oxygen atoms in our formula there, so that works out relatively well. The other thing that we need to think about here when we start plugging in double bonds or rings is we need to think about the index of hydrogen deficiency and make sure that our structure fits that. So the index of hydrogen deficiency is also known as the sum of the rings plus the pi bonds in the molecule. And this is a formula where if we have a structure that has no formal charge, we can use this formula to determine how many rings and pi bonds there must be by looking at the number and type of atom there. So the formula goes 2 times the number of carbon atoms plus 2 minus the number of hydrogen atoms minus the number of halogen atoms, x, plus the number of nitrogen atoms, divide all that by 2, and that will give us the total number of rings plus pi bonds in the molecule. So if we do that for this structure, we would have 2 times the number of carbons is 5, plus 2, minus the number of hydrogen atoms is 9, minus the number of halogen atoms is 1, plus the number of nitrogens is 0, divide all that by 2, and what you're going to find is that the sum of the rings and the pi bonds is going to be equal to a grand total of 1. So what this is telling us is that the structure has 1 ring or pi bond. It doesn't tell us whether it is a ring or a pi bond, it just narrows it down that it has to have, the correct structure will absolutely have 1 ring or 1 pi bond in it. So that 1 ring or pi bond could very well be accounted for by this carbonyl group here. So that's giving further evidence that this structure could very well be on the right track. If instead we'd calculate index of hydrogen deficiency and it had come out as 0, that would tell me that we need to go back to the drawing board and draw something that does not have a carbonyl. But that index of hydrogen deficiency of 1 suggests to us that the carbonyl group is perhaps properly positioned. So now that we have that part or piece in place, we want to know, what is this CH2 group coupled to that's causing it to appear as a triplet? And looking at the spectrum, there's really only one possibility that is likely relevant here, and that is that it is directly bonded to this CH2 group at 3.8 ppms. That is in green. So if I plug that green CH2 group that was at 3.8 ppms in here, and I think about what the multiplicity of it was our triplet at 3.75 ppms. And if that was coupled to our triplet at 2.75 ppms, that would make sense, because if we have a triplet here, that means 2 vicinal hydrogens right here. If we have a triplet here, that means 2 equivalent vicinal hydrogens over here. And we could compare the coupling constants for those. So we could take up here at the top, and to sort out the coupling constant values, we will subtract there for this triplet the most downfield value there, 1877.3 minus 1870.7. If you do that, you come up with a coupling constant of 6.6 hertz. Do the same thing again for our triplet here. Pick two of the adjacent signals to determine the difference in hertz values for, to determine our coupling constant. And we get, as good luck has it, a coupling constant here of 6.6 hertz as well. So that suggests to us that these two are indeed coupled. And so that gives me further evidence suggesting that we are on the right track with this piece of the structure. So we had previously pieced together this carbonyl bonded to two CH2 groups. We had also pieced together this ethyl group here as well, CH2, CH3, and that would actually encompass all of the proton signals here, because looking at the 4 proton signals, we've accounted for 4 types of protons: our methyl group, CH2 methylene in blue, CH2 methylene in green, CH2 methylene in black, and then our carbonyl. So now we need to figure out how to stitch this structure together and incorporate the necessary atoms here based on these substructures, based on these parts and pieces that we have. So as luck has it, the parts and pieces that we have stitched together so far, which I'm drawing out here, account for all of the carbon atoms within this molecule. So the formula is C5, and we indeed, in the right-hand side of the screen here, have accounted for a total of 5 carbon atoms. So we've got all the carbons taken care of, our 9 hydrogens, 2, 4, 6, 7, 8, 9. So we've got all those taken care of, and we've got 1 oxygen taken care of the 2. So what we have left to add is that we need to add 1 oxygen and 1 chlorine into these structures. And now to sort out where everything is going to go, keep in mind that everyone has to have a complete octet. And so what that means is that this CH2 group here is not yet done. I'm putting a box there to indicate we need to fill in something else there to get it at its complete octet. The other end of this group, the CH3, is all good to go. That is going to be one of the ends of the molecule because it already has a complete octet, so we don't need to add anything there. And then looking at this substructure, we have something that we need to fill in there to the left of the carbonyl because that carbonyl carbon does not have a complete octet. Likewise, at the right-hand end of this substructure, we need to fill in something else there because our CH2 does not have a complete octet there. So what do we fill in into these boxes to get a complete octet and use up 1 oxygen, 1 chlorine, and make the chemical shift values work out? Well, looking at our data here and our structures, what we would expect for this is that we need to do some trial and error here. So we have 1 oxygen and 1 chlorine left, and we have 3 slots to fill here, here, and here. So one of these has to overlap, meaning that we're going to fill in something here adjacent to the CH2, CH3, and then that's going to be the same atom that stitches us into the other system. So thinking about the 2 possible ways to do this, we could either place an oxygen atom here and a chlorine over here, or by process of elimination, chlorine could go here and oxygen could come over to here. One of those 2 possibilities has to be the right way, and then onward from there, we would connect to the CH2, CH3 group. And so thinking about which of those is the right way, we can draw out the 2 possible structures that we would generate from this. I'm going to draw those down here in the lower left-hand corner. And we're doing this process of elimination, this trial and error business here. And that's one of the things that's really frustrating and really exciting as well about solving NMRs is it's like solving a puzzle where you can be really frustrated about it and you can be like, this is never going to work. I'm never going to be able to solve this. And then eventually when you solve the puzzle, that part is super gratifying. So Just be patient with it and be willing to try different things, sketch out different things, and use lots and lots of scratch paper, to be honest. So here, plugging in a chlorine atom at this end of the molecule, that's following this first template here. And then we'll do an oxygen at the other end. So an oxygen at the left end of this molecule, just to the left of the carbonyl. And then one of these two ends of the structure that we've drawn here has to be connected to the ethyl group. And the only place it can connect is over here at this left end, because at the right end we have a complete octet. The chlorine is going to be the end of the molecule there. So I'm going to plug in my CH3, CH2. So that's one candidate structure. The other possibility is we could try to orchestrate this in the other way, which is that I'm going to plug in my carbonyl group directly bonded to my CH2, CH2. And from there, I'm going to put an oxygen at the right-hand end this time, rather than a chlorine. And at the left end, I am going to plug in my chlorine atom there. So in this scenario, now that we have filled in this part that I'm highlighting in the upper right-hand side here with the oxygen on the right, chlorine on the left, oxygen on the right, chlorine on the left, now the ethyl group has to plug on there somewhere, and we could plug that onto the right-hand end of the molecule here. CH2, CH3. So now we have two candidate structures, and we have to ask which one of these structures do our data fit for. And so asking which one of those our data fit for, we can go through and evaluate things like the chemical shifts and the multiplicities to answer that question. So looking at the structure on the left side here, if we think about which is which here, which carbon atom, which hydrogen, etc., our CH3 group at the very end here was the furthest upfield, the most shielded. It was at about 1.25 ppms, and it was a triplet. And this would make sense based on looking at our NMR spectrum and seeing that we expect saturated alkanes to show up around 1 to 2 ppm. It's very well shielded, very enshrouded with alkyl groups. We come to the next position, that's our CH2 group right here. And we said that due to the fact that the methyl group here was coupled to a CH2 group, and that CH2 group that it was coupled to was the one over here, the quartet, which was our furthest downfield signal, that represented a signal at 4.2 ppms. And that was a quartet. And so far, this is all adding up. This is all making sense. That would be at 4.2 ppm and a quartet, based on the fact that it's the 3 vicinal hydrogens from the methyl. And it's at 4.2 ppm, very downfield, particularly downfield, because it is adjacent not only to an oxygen atom, but then it's one further bond away from this carbonyl group that's also going to act to withdraw electrons from it. And so downfield it is. And then from there, we can match that up even better with a group from our chart here. In our chart here, we see ester specifically, and now that we have an ester group in this molecule, we can look at the ester range, and the ester range is between about 3.5 and 4.8. So we are smack dab right in the middle of that. This is really spot on for an ester group, and we indeed see an ester group in this molecule. So that's a really good sign that this structure is perhaps on track. We come on down the line here, and we get to the CH2 group that is adjacent to the carbonyl, and we had assigned that as our 2.75 ppm triplet. That signal right here was what we came up with earlier for that, and that still makes sense that that is a triplet because it has 2 vicinal hydrogens that are equivalent to one another. And also 2.75 makes sense because as we look at our chart here and we look at that 2.75 region, we are really nicely in line with the situation where we have a carbon hydrogen bond that is adjacent to a carbonyl group. So that's going to work out very nicely there and make sense for our 2.75 ppm triplet. And it's going to be at the relatively downfield end of that range because of the fact that not only do we have a carbonyl nearby, but at the next position we have an oxygen of that ester. So that's going to make that at the relatively downfield end of that range. So all makes working out now. And then we come here to a CH2, and that CH2 is going to be the guy right here. And that shows up in our spectrum at 3.75 ppms as a triplet, exactly as we would expect. And so this structure is going to be a really great match for the data. The structure on the right is not going to be such a great match for the data because when we look at it and we think about the downfield chemical shift of the carbon and hydrogens that are directly bonded to the chlorine, that's very far downfield at 4.2, and here we're not going to expect this ether group to be pulled downfield quite that far. So that's one reason why this structure is going to be inferior to the other one. Another thing to keep in mind is that when we are looking at organic molecules, functional groups are so well known for a reason. They're well known for a reason because they are themes that occur all the time in organic molecules, be they naturally occurring organic molecules, be they synthetic molecules, whatever the case might be. And so anytime you have a situation where you can piece together common functional groups like an ester group into a molecule, that's very often going to be the correct way of going about things. Also, if you think back to chemical stability from organic chemistry, the acyl halides are quite unstable and reactive, and so you might wonder if that's the real structure there. If this is a compound that's been laying around for a while, quite possibly that would have decomposed through reaction with water. So that's a practical consideration when thinking about some of these structures. But ultimately, our best match based on the data is going to be this structure in the lower left-hand corner. So what I hope I've illustrated here is that when you are determining the structures of organic molecules, you need to focus holistically on the chemical shift using the chart as your reference guide, the multiplicities to make sure that they match up with the number of vicinal hydrogens or the expected splitting pattern if it's a complex splitting pattern, including you can use the coupling constant values if those are available to you as another piece of evidence for which hydrogens are vicinal to one another. And then also be sure and take advantage of the integral values that are listed for you here to determine how many hydrogens compose each signal so that you know whether you're dealing with a CH group, a CH2, or a CH3 group. So the worksheet package that I have for you has a wide variety of other problems that are similar to this particular problem. In some cases, we incorporate other types of NMR data, such as carbon-13 data, or two-dimensional NMR data, which we'll get into in the upcoming videos. And what you should be able to do with those is piece together a reasonable chemical structure based on the information that you are provided. This is very much like solving a puzzle. It is a skill that you have to practice and that does involve some inherent frustration to it. And much like riding a bike, it's the sort of thing that you have to keep turning and cranking at and maybe fall off of a few times before you really get the hang of it. So practice makes perfect. Keep at it, and you will be surprised with how proficient you get at solving structures for molecules.